All right. So we are live for part 5 of our Synacor challenge and exploration. Um, so I think we start with a little bit of a recap, get our bearings here. Um, Last time, so we went into the text adventure, and we finished the last puzzle in there. Well, that's in the vanilla adventure, and we reached the end. And the end gave us a very special message. Where's that book? Um, well, I'll pull it up in a minute. But anyway, there's a book explaining the architecture of well, no. It's explaining the physics of the world, which was it was referencing all the registers and saying that these 8 registers control the state of the universe. So the physics of the world is controlled actually by the architecture of the VM. So it's talking a little bit about the universe and what needs to happen for teleportation to be a thing, and how a teleportation machine would work. Um, and so, in order to in-game, in-universe, get teleportation to work, we need to be able to step out of the universe of the game, from within the game, or I don't know, maybe not necessarily from within the game, but we need to be able to step out of the universe and rewire how the universe is wired. So it gave us instructions for what to do with the actual architecture, and that means now we're left with some ROM hacking. Um, what else happened? Okay, so in order to enable that, we started wiring together an emulator layer that's distinct from our VM state. So our VM state is it's really nice for running the VM like one tick at a time, executing an instruction, doing all the state transitions that are required by instruction, right? Like popping from the register and like dereferencing dereferencing the register reference, getting the value, doing the addition, and then saving to memory or whatever before you like move your instruction pointer and do the next thing. Right. So we made that really nice. Um, in fact, we even gave our state transitions little phase names and type restrictions so that you can only move to a phase if you're already in a certain phase. So, if you forget to move the instruction pointer before readying up again for another instruction, then that's just a compilation error. So that's a whole series or a whole class of bugs that just aren't representable anymore. We also did this. So this is what every step of our VM looks like, right? We're either halted, we have output to provide, we require input, or we are ready to simply continue. Um, yeah. And of course, that includes here some exit codes that we start to build. This is the success, of course, and everything else is pretty much can be some other error code. But I don't think we'll run into those too often. Well, now that we're thinking about injecting bytecode into the VM, we might start to run into those kind of errors. So it'll be nice to have actually. But I think the ROM in and of itself shouldn't be having those errors. It was probably compiled properly. And is honest about its constraints. Okay, so we have that. And this is nice to work with at the low level, but at the high level where we're working with a console, where we're interacting with a game, this is too granular. So I started making this emulator layer, and this right now you can do 2 things. You can feed it an input string, so this is like a command to the game, or you can just let it run and take all the outputs. And now every time we're at this requesting input stage, then we take our current tick and we add it to our history stack. That way we can also backtrack, rewind, and execute a different command. right? Like we could do something that gets us killed, eaten by a Gru, and then we can rewind. Um, yeah. And then this I'm using in our main method. Underneath just a very simple, while loop, right? So we'll take, we get the output, the next output, and then we will, what do we do here? Yeah, so we take the output, we print that out, and then we read in the next input. And depending on that input, now here I've added, this is kind of where we'll start injecting our own codes. So this is like a example code for now. But in the default case, we just send that, we feed that into our emulator. Okay. And so with that, I think we're ready to talk about what we want to do with our wish list for today. So let's try that. For our wish list, you've got these things, that's good. We don't care as much about the state transformer, but this emulate at a higher level so we can explore, diff, inject VM states. So what kind of things do we actually want to do? We want, say, ability to rewind state. Ability to inspect. We could inspect the state. Now maybe this we wouldn't actually do. Like we can just do it in a worksheet or play with a worksheet. But if we have an emulator for which we can save history, then we can just interact with that with code rather than commands from the console. So that tells me another kind of to do. We want functions that are independent from command, from like REPL command for the worksheet, right? What else do we want to do? Obviously, there's injecting some state. We want to be able to inspect the memory. I think we need a nice way to print. So like we need the start of a disassembler. Disassemble bytecode into something readable. That way we can start to understand the structure of the program that's running. Maybe we want to be able to diff to states. Yeah, I think we might want to do that. So many things. For a little bit of motivation, let's go to our worksheet. And in the worksheet, I have the prompt. So this is from the strange book. Oops. Okay, so let's reread this. This is basically where we ended last time, and this is what was motivating our emulator layer, because now we basically want God mode for the game, right? So recent advances in interdimensional physics have produced fascinating predictions, yada yada. So the state is controlled by registers. Lower registers control mundane things like sound and light. The highest, 8th register, is used to control interdimensional events such as teleportation. Okay, so we need to be able to set the 8th register to the right value. At its minimum level, when it's 0, And it assumes the user has no way to control. So I guess what we first want is a way to control the 8th register, right? So we could say that in our README. And that can be like kind of top of the list. Like ability to rewind, I don't know, like we might test that. Oh, I want the ability to replay commands. So as we're inputting commands, save them, then we can take that list and just use it as basically a save state when we're running again from scratch. Or like we could figure out how to serialize state. I think this works better. So this top one is ability to set the 8th register. And then everything else will basically be in service of exploring the machine code and figure out what the value in the 8th register should be, because we're not going to brute force it. I mean, we could attempt to brute force it, but I imagine that's not the intended. I imagine that's made harder than necessary, or harder than is like tractable. That's also not the fun way. We'd like to actually understand what we're doing, right? A problem isn't really solved until we have like a distillation of our solution, which is a part of why I like to do like a model distillation step so often. Oops. So there's the default. Great. The second destination requires a very specific energy level. The teleporter must take great care to confirm that this energy level is exactly correct before teleporting its user. Okay, so the teleporter does spend time verifying this level. So in order to be able to figure out how it's verifying it, we need to figure out like where it is. Like we need a log of the bytecode that's running. So let's see. Log running bytecode between two states. Right, and then after logging that bytecode, disassemble said bytecode into something readable. And PC locations, all the counter locations. Yeah. Let's look at this a little bit more here. Okay, a teleporter would need to test the energy level on the 8th register. So we're going to look for that test so that we can get the right value. And I suppose we can run that test simply by changing the value of the register and letting it try to run. If you find yourself trapped in an alternate dimension with nothing but a handheld teleporter, extract a confirmation algorithm, re-implement on more powerful hardware, and optimize it. And by powerful hardware, that means just in our own like JVM runtime rather than the Synacor VM. Then set the 8th register's value, activate, and bypass. Okay, if it's set correctly, you should be experienced. If it's set incorrectly, the now bypass confirmation mechanism will not. Wait, bypassed? How can we have a bypass confirmation mechanism? Like, let's see, search bypass. Set the 8th register to this value, activate the teleporter, and bypass the mechanism. Oh, so we want to bypass the mechanism altogether. So it's probably too expensive to run at all. But letting it run will at least let us know what it is that it is trying to do, so we can log that code. And then, yes, and then engage our cosmic override. Hi, Zeno, how are you? If the eighth register is set correctly, no anomaly should be experienced. Okay, so we're allowed to set incorrectly because we're bypassing it. And if we're bypassing it, we could end up in this weird place, which I do want to try going there and seeing if I imagine we might still get a code, but that it's incorrect. The hash might be wrong. Okay, so what does that say for our to-do list? Let's just look over everything again. So ability to rewind state, this is basically just us testing our emulation layer and making sure it's at a nice level. Ability to replay commands, this will be nice for convenience. As far as like getting to a specific state, it should be very easy to add that in. Just log our commands as we are sending them. Ability to set to the eighth register. Okay, this will be important. This will be our first like thing we do that actually makes it possible for us to do teleportation, right? And then log the running bytecode. We'll need this. So basically diff between two states to figure out what bytecode is running. This will help us find what it is that we need to disassemble and then try to turn that into something readable. And then we just stare at, we stare at assembly code, not bytecode. We start assembly and try to figure out what function is being run, how it recurses. Okay. So let's revisit our emulator. And I think we want to just make things a little bit nicer here now that we've had a chance to sleep on it a little. Um, so we've got our in and out loop. Now, something I don't like about this out is that it returns both the string and the tick. It's a pattern I use often, but I don't like using it here. I'd like to just return the tick and put the out into perhaps like an output buffer because we're not necessarily using it all the time, right? So I want to consume it at will. Um, and I just like to have a chance to play with something from scratch here, so we make sure we're understanding how to do something in this emulator. So we'll do. I wanted to try something like this. So progress until locked, and then this would just give us our next emulator state. And as you're watching me do this, if you don't think this is a good abstraction, let me know because I have a tendency to go down rabbit holes sometimes. Yeah, yesterday's code kind of was melting my brain a little bit too. I did this little refactor here. So we started with the unfold nonsense, and then I did a mutable thing, and then I did this right after the stream. I should have just done it on stream because this made it actually really easy to think about, right? So it's just a recursive loop, and if it's continue, we keep recursing with a new tick. If it's output, we do like save that output, and otherwise we're there, we're done, we're at the end. So this is our base case here. So it turns out that's like very simple. So if the code is melting our brain, then it's not good code. um, before we do this, I think we need to have like an output queue. So out queue. Yeah, got an output queue. It's gonna be an immutable queue of string. I've already imported queue. Where did I use it? Oh, right. Yeah, I use it here. I was doing this onto a list, and a list makes it go backwards, so you have to use a queue instead. Okay, and now when we build this output, I guess we're gonna do the same kind of thing. So we basically just keep ticking along, keep ticking along. Anytime there's output, we take it. And once we hit any of these two states, we are blocked. In fact, we could even say, maybe we formalize that. I don't know if this is something we'll use often, but it's worth at least jotting down the idea in case we do like it. So let's look at our types of state. Okay, so tick. So def is blocked equals this match exhaustive. And basically, we can do, if it is halt or input, then we're blocked, right? And then if it is output or continue, we're not blocked. So is blocked, this is true, and this is false. We still have to match on the particular one here, but now we can say like t if t dot is blocked, then we do that, right? Or like that can be an assertion that t is blocked in case we do end up adding more ticked states. You don't need programming, but you're an IT student. Should you be more stressful? What do you mean by more stressful? You don't want your job to be too stressful, or you don't want it to be too exciting if you're working in IT. Excitement usually means something bad is happening. So emulator here, I'm not sure. I suppose there's not necessarily new output and feed, so we'll just output queue can stay the same. Or rather, this can just be copy, and state equals next, and then history equals that. Right? You don't even need to. Okay. In this case, though, with the output queue, all we're really changing here is that we take our emulator. So we run the loop that gives us a queue of output characters. We take that output into a string. I guess it's already a string at this point, right? How does that make string? So we take our emulator and output queue dot enqueue our new output. Okay, there we go. And then we have to have a way to consume output. So def consume, or let's call it use output. So this we can just hook into our main. Well, let's look at our main. Right, so here in our main, we are doing like a print line out. And what I want to do is just make that give us a place to use that print line. So we're going to give a function that takes an output and returns unit. So this is just a side effect. And that changes our emulator state. So it consumes the output string. Absolutely, yes, you can learn programming on your job. So let's look at we need our next output from our output queue. So val out, and then the remainder is going to be output queue.dequeue. Right, so this is kind of like the tail. And we're going to copy our state, but output queue is just now outs. So we drop that one output, and then we run our f function on out. Okay, and now here's the payoff. Here's the code that we get to clean up. Here, so we have an emulator, and we keep changing the state of the emulator. So here's the start. Now we can do emu equals emu dot not next out dot consume. What's the new function we made? Progress until blocked, right? So progress until blocked. And then we can use our output. So we're not being forced to use the output, but we can do emu dot use output with print line. Now we don't need that. I suppose we do still need like the format to do format. And then in here, which I'm just going to remove, oops. Yeah, I'm going to remove a bit of this and just match directly on the read line. And then here we set emu to next feed our command in with a new line at the tail. Okay, great. So that's kind of like how I want to use our emulator, right? So rewind might be like, I guess like this loop. Why is that no loop? Oh, no, there's no loop there. We'll just do like emu.setRegister, or rather emu equals that set register. So we still have like an immutable emulator state. Yeah. So maybe from here, let's try a history to make sure that we're a history modification. So we'll try the rewind or undo to make sure we're able to work with this emulator properly. I like the idea of having these bang commands, but maybe something easier to type, maybe just having the words themselves. I don't like rewind. You can name it undo. Or I don't know, like slash undo. Yeah, slash undo, as if we were in like Twitch chat or something. That's easier to type. And I had an idea that when we halt, we don't actually want to halt. We don't want to exit this loop because we want to give ourselves a chance to play with that and actually rewind things that we aren't halted, right? Maybe the emulator hit a halt because you got eaten by a grue, but then you can still say undo, right? So this is going to be something like emu equals emu dot I suppose undo works. Let's implement that. So I'll implement undo. And I suppose we don't need this next out here anymore. So def undo. And what we get is another emulator. And basically we pop off of our history stack. I think we can just fail silently if there's nothing to undo. That shouldn't be like too surprising behavior, right? So we'll do history.head option. So when there is a past, then we'll copy. So our current state is now past. And then our history is now history.tail. The output queue, though, I'm not sure that works for our undo. Maybe it should be tracked outside of the emulator, because rewinding the emulator is not the same thing as rewinding like the VM state within it. I mean, we could try this. We could try this. Hey, how's it going? What is the plan tonight? Glad you asked. So let me pull up our README here. I don't know if I've updated this yet, but it is also there in the Synacor link. That's on the Twitch side, though. I don't know if that prints in a nice way on YouTube. Maybe I can copy the message. Well, we'll figure that out in a second. But this is all also online. So tonight, we've gotten to the state within Synacor where within the text adventure, we reached the end of what you could do, and we learned about a teleporter. And in order to teleport, you have to do physics within the game, right? So there's a book about physics in the game, and the physics is really talking about the registers that are running the VM. So it says there are registers that control the state of our universe. So that's telling us that we need to, in order to progress in the game, we need to change the values of the registers that are that the game of the Synacor VM that the game is running on, right? So in order to do that, we have this emulator layer that we're building that can give us kind of like a God mode shell into the game and allow us to do things like undo an action, ability to rewind state, ability to replay our commands that we entered previously. So that'll just be like a little nice to have. And most importantly, the ability to set the value of the 8th register, which is what controls teleportation. And in order to do that, we'll need to eventually be able to dig in to the bytecode. So I want to be able to log what's running and then disassemble that bytecode into something readable so that we can reverse engineer. Right, so this is for reverse engineering. So basically, in a sentence, we are reverse engineering the game so that we can go on. Oh, the stream is vertical, so you can't see any of the text. I think if you click into it, you can get into the horizontal version of the stream. That's like a new feature YouTube has where they do like a vertical feed of your stream as well. Yeah, I'll have to look. I'll have to take a look at that and see what that looks like and see if I can mess around with it a bit. But yeah, I can also copy the copy the text into chat, into the YouTube chat, so that you have that. You know, we are not emulating any physics here. So the game has its like in-game physics. The game is a text adventure, right? So the game is a text adventure, and basically we just all we have to do is change values around in the running VM. But this is a completely foreign machine architecture. So this VM has secrets hidden in its binary that we have to uncover. Okay, here we go. For the people on YouTube, I appreciate seeing people from YouTube, by the way. Definitely no treasure within. Oh, right. So here what's on the left side of my screen, if you can see it, is the running Synacor challenge. And like this works. It's a text adventure. You're given a prompt. You find yourself standing at the base of an enormous mountain. A sign reads, "Keep out. Definitely no treasure within." So from here, we can go south. We can get the tablet or take the tablet. You can use the tablet to write some words. We can move through the doorway into a dark cave, right? So classic retro text adventure. We don't need to run this yet, though. At some point, we will run that long enough to... We'll want to run through it one more time, just so that we can get to the end state where we have the teleporter. And then we'll save that output so that we can basically jump quickly to that state and mess around with it. So, on the agenda right at this moment is creating an undo command. And we have one. It has potential issues. So, because undo only works at the level of the VM state, of the VM state ticks. So that might get us into like inconsistent state with output if we're not constantly consuming it. But as long as we consume the output, then we'll be fine. Okay, so emu.undo, and then we reset the loop, right? And then go back to progressing until blocked. So I think that works for us. In fact, that's a very straightforward implementation. I think we can just run with that and see it work. Right, this is basically a couple one-liners to do that. So let's exit here, and we'll run from scratch. Oh, we do have some compile errors to fix real quick. Let's do it in here. Method head option does not take parameters. Oh, right, we're gonna map on that head option. There we go. That should make the compiler happy, yeah. Map, not yet or else, just this. So we either make a new state with the history truncated, or we just return this state if we can't actually go undo at all. And we have issues in our main method, so let's look at that. Here, emu equals next.feed. No, emu.feed. Feed in our command. Okay. Now let's run that. There's still an issue here. Oh, right. I think we need a nice way to initialize an emulator. So let's add that in here. So object emulator, companion object for a class for adding definitions like def init. So given a starting state, start VM state, we need an emulator from that. And that can be use that start state. Our history will be empty. Our output queue will also be empty. And that's pretty straightforward. So emu equals emulator dot init from the start VM state. And you know what? I can just kind of inline that state here because we don't need it anywhere else. So we'll keep it out of scope of everything else so we don't confuse ourselves. Mm. Mm. Okay, there we go. And with that, missing type parameter for Synacor VM state. Oh yeah, start, it needs to be a ready VM. Oh, we required a tick. We actually required a tick. Oh, no, start is a tick, not a VM state. Right. Okay. Well, then we have a warning here, but you don't need to worry about that. That's basically just saying that this is an exhaustive search, so we need a case like this. Okay. Now let's run it. And I want to see that we're able to undo. Give it a sec to compile. I'll make it bigger. Okay, so let's go through the doorway. Let's do something that's irreversible. Oh, this is weird. Oh, we have broken it. Well, that's not a good thing because the re-architecture should have made it easier not to break things. um, okay, so we seem to be printing the same output line, which means we are not actually progressing. So we read a line, we send that command in, we go to feed. Feed we never changed, so that should still be fine. And then from there, right, we are resetting emu over here. So that should be fine. Let's look at our symptoms a little bit closer. We get the welcome to Synacor challenge message. Then we go through the doorway and we keep getting the welcome to Synacor challenge. Now let's do something else like look. Okay. And we're getting the same thing. I'm gonna go back to, let's see. I liked when we were printing one character at a time with a little delay, but we don't have that in this architecture. I suppose I could play around with this in the worksheet and see what is going on and compare the VM state. So yeah, let's get this running over there. That should be enough to work with. Okay. So we're building our state. Well, start VM. It's gonna be this. Or no. I think I want just this bit here. And then we can wrap that in the continue tick. Okay, let's take this emulator and let's progress until blocked. And that gives us a new state, right? So let's look at the tick after that. Or progress until blocked gives a new emulator. And I think this might be where our issue is. So dot state after that. So let's compare that with the emu.state. And let's see if those are equal. Okay, so those are not equal. That's good. But let's see what they actually look like. I need a full diff here. So the states of these two are different. This one has no history list. This one here should have a history list. Or no, this is just the VM state altogether. So we are at 0. Our program counter is at 0. Right, and here, I know, let's print line that. Doesn't seem to be. Okay, and here for the second one, we've got an input tick, so it's waiting for input. So wait, that doesn't have a state then. Yeah, you can't get the current state. Progress until block gives us another emulator. Oh, right, and then its state is a tick. And this particular tick is an input tick. um, what else is in an input tick? So let's take a look at ticks. Yeah, it is just a function from character to a VM state. I think I kind of want to have the state in here, so we'll think about that a little bit to do include VM state. Probably. But let's look a little bit more closely at our emulator here. When we progress until blocked, we run this loop to get the next state. Next state is defined as a tick that you're at when you're blocked. So this tick itself must be a halt or an input tick, right? Okay, so we can. I think I'd like to write this as an assertion here, so we can assert that, or next, assert that next dot is blocked. Just to sanity check ourselves. And we add our out to the output queue. And then we consume that. So when we consume that in our main, oh, this is the wrong main. When we consume that, so we use the output, Using output. Oh, right. The output was never used because we are still immutable here. Um, yeah, maybe it's not a great idea to have like immutable values here in like a mutable loop with vars. I don't really like mixing mutation and um, immutability. It's not something I'm used to thinking about. So, good note there. Maybe change how that works. That can just be a loop, a recursive function. If a recursive function is tail recursive, the bytecode that it emits is just about as performant as a while loop. So like either of them are faster than doing like a map or a for each function calls. But you have to make sure your function is actually tail recursive. Okay, so now let's go through the doorway. We go north, keep going north, and then there's a bridge. So we continue through the bridge and we fall down. Now at this point, normally we can't go back up, right? But now we can undo or slash undo. I don't think we undid far enough because basically we just repeated our state. Okay, so back to the drawing board there on undo. Now what are we adding to history? So the state that we're adding to history is the state before requesting input, right? That's the state we want to jump back to. Now, the problem, I think, is that we're also doing the same thing when we progress with output here. I don't think we want to. I don't think we want to save the state after all the output, and then also save the state before all the input, because in that case, you just go back to the state where we printed the output, right? And you can't actually respond to it. So this part should just be history. Yeah, and that's interesting because now we are still progressing our current state, but we're only saving certain snapshots. So the history, this is teaching us, I like this moment because it's teaching us a little bit more about a model. Our history isn't like the history of everything we've ever been. This is a snapshots of input requests. So like maybe we even rename that to make it more clear. Try Catch TV, welcome. Thank you for the raid. So, how's your stream? Was it a good one? I've seen you live a few times, but I haven't been in there lately. I don't know how many of you are familiar, but we've been working on the Synacor challenge. So this is my way of continuing Advent of Code through this season this year because there's only 12 days. Synacor is also made by Eric Wastl. I'm doing great. I'm having a good time. So we're starting to get into the really fun part of you're working on migrating a WordPress site. Okay, cool. Good work. Over here, we're starting to get right into the fun bit of Synacor. So this is also created by Eric Wastl. So he created this like a few years before he ever did Advent of Code. And what this is you're given just a binary, a compiled binary, and instructions or like a specification for a VM architecture, right? So this binary is for a foreign architecture. We can't run it. until we first implement a VM that's capable of running that bytecode, right? So we've done that, done the VM state, added like an emulation layer, and we've run the program. And what the program is a text adventure. And as we're going through this text adventure, like we solve some puzzles, we get to the end, then we learn that we need to be able to teleport. And in order to teleport, um, we need to know about interdimensional physics. And how interdimensional physics works in the game world is that there are registers and that control the state of the universe. So the registers are the registers of our VM. So now in order to progress in the game and be able to teleport, we'll need to do some sort of like ROM hacking bytecode injection in order to like basically it gives ourselves like God superpowers within the game by being able to directly interact with the VM. So that is where we're at there. And more specifically, I'm testing out my emulator by implementing an undo function that allows me to go back past like you fall off a bridge. Well, can you undo that? Can you rewind that state? So we're gonna try that out and test our God mode powers. Right. So I was just looking at our output, and what we're just realizing here is that our history that we track in our emulator, our history of important ticks, is only going to be very specific ticks. We only care about ticks, VM ticks where input is requested. So we'll rename history in just a bit. Now output Q equals that. So we're going to copy state equals next. We progress a state, but we don't do anything with our history queue because we don't really care about the state before all of that was mentioned. So I suppose we do still need to. No, I think I've got it backwards. I think the state we want to save is a state right before they do a bunch of talking, not the state right before we do a bunch of talking, because we want them to replay that speaking before we then respond. So I've got that backwards. Okay, so here we prepend state to our history, like the former state, like our current state, we prepend it to our history once we're evolving to the next state, right? But when we're feeding input, I don't think we want to add the history in this case. So here we only change the current state to next. Okay. I think I'm happy with that, and we can simplify this a little bit. I think that's straightforward enough. And let's just give that a run. Okay. So let's go through the doorway. Go north, north, and there's a bridge. So let's go there. We're gonna fall off the bridge. And now slash undo. You're standing in a cavern full of bioluminescent moss. Wait, undo set us back to what exactly? After undo, we progress until blocked. I think we want to undo further than that. Because what just happened is we progressed until blocked, right? And then we saved a state. So the game said something to us. we saved the state right here. And then we said something to the game. And the thing that we said to the game was undo. And so we still progressed our state, right? We progressed our state after doing all this printing. And from that new state, that was a blocked state, right? So it's a blocked state from which we can talk because it's blocked waiting for input. We talk to it. The thing we say to it is undo. And when we say that, we drop some of the history. Oh, we're not dropping any of the history. Okay, let's go back to that here. Wait, are we? So when we undo history.ed option, past. Okay, so we're saying that the previous history becomes our current state. Right, so the thing it said right before we said fall becomes our history, becomes our current state. So it's going to be right again before we said fall. So it's basically going to replay what just happened. So we actually need to drop 2. That's interesting. So yeah, we need to go back 2. Well, let's try that. So we're going to take our history and we're going to match on that. And we want a case where there's a thing that we're ignoring. And then there is the past. And then there's older history. Right, and in that case, we copy our state where our current state becomes past, and then our history becomes older history. That's what we actually want. And then if there's not that much history, any other case, we just don't do anything. So we just return this. And I don't know, we could say a message, not enough history. We'll just make it a comment. We're fine. That's reasonable behavior. Okay. So now let's try that. This isn't big enough, is it? There we go. That's better, isn't it? So now we go through the doorway, go north, and off the bridge. Continue. Now we fall. So that forces us to go down. And now we can undo back to falling through the air. We can undo further. So from falling through the air, there's only one exit down, or the other exit is undo and run the rope bridge. Great. Awesome. So we unlock time travel. That's very satisfying. Okay. Now there is one little issue. Actually, it's no longer an issue. I was gonna say I was worried about the line wrapping, like it wasn't wrapping properly, but this line wrapping is fine. That works. So we don't need to do anything smarter than that. There's a stylistic issue I want to fix though. Eh, but just to make things more authentic. We've got to go back to printing characters with a little delay. So it looks retro. We gotta make it look cool. We can't just have all the text show up at once, right? You have to have a little bit of atmosphere. So we'll take a quick detour here. Def type. Oh, wait, type's already a keyword. I know. We'll call it type line instead of print line. So this returns a unit, and we take a string, and we're gonna take string dot for each character, we are gonna print the character, and then we're gonna sleep for 5 milliseconds. And then after the end of all that, we do our print line. So instead of print line, we're gonna do type line here. Oh, we've got an issue here. Oh, sleep. Yeah, we gotta do thread.sleep. I think that's still a little bit too fast, isn't it? Yeah, let's make that 10. Maybe that's more visible. Why is it showing up as whole lines? Is this like SBT not printing things out unless... So there are these info message, right? We're printing out the standard out. Oh wait, no, info. Doesn't this mean like standard error or something? It looks like SBT is kind of forcing us to have a full line before it'll show any input, which is weird. I don't know how we were doing it differently previously. Right, you notice how the longer lines take longer to print? So it's still waiting, but it's not showing the character as it goes. Looks like it might be line buffered. You may need to flush each individual character. Ah, okay. Well, let's see. I need to turn on Copilot for that because that's not something I work with often. Okay, flush each character. Um, so it shows up in output and print console.flush console. What am I printing line on actually? So this is console.println. And what would be the default output? So a console does all this. There is an out, error, and in. And I suppose when we print line, we're using the out. So what does flush do? Flush is the output stream when partial output has to be made visible on the terminal. Okay, great. So we flush that, and then we wait. So thread.sleep 5 milliseconds. And then we do the print line. Okay. Thank you for that debugging. It also seems to be suppressing some new lines. Good to know. Nope, that's still not happening. I think this is an SBT thing. Let me see. Chat. So maybe here I'm gonna pull this out into Windows so we can see what we're saying. Okay. So maybe this is an SBT thing, but I'm trying to get a message to print one character at a time with small delay. Right, like we did this the other night and it was working just fine. So this might be, is there an SBT thing forcing it to print a whole line at once? Flushing doesn't seem to work. Okay. Let ChatGPT do that. Or that's not ChatGPT. That is GPT in the background. This is not crucial. But I know we want to do this in style, right? The point is our undo works. And now going back to our list. Rewind state. So we'll say partially. We can rewind state. There may be other things we want to be able to do with that. We want to be able to replay commands so that we can quickly get to a place. That's not too hard to add. So we'll just do that right now, huh? So back in our emulator, every time we run an input, we can just add it to like a command history. But what happens when you redo higher level commands like undo? It's not going to end up here because we're not actually feeding it here. And undo specifically would kind of like make this command history unreliable. So maybe we don't store it in our emulator. Because ideally this is supposed to be a list of commands that gets to this state. Or, you know, like when we do undo, we can also drop from our command history. Yeah, I think that's what we'll have to do. So to do drop command history. And now we have a command history on top of our output queue. So input history is what we'll call it. And can this just be a list? I think it can be a list. You know what? Let's make a queue so that we're appending to the right. Oh, someone's got it. OBFM Macaw. SBT has an option called output strategy, which you can set to some standard output when you use the fork option. And that will get rid of all the infos, but you may have to force wrapping again. Oh, okay. Thank you. I appreciate that. We'll get there in just a sec. So we'll finish this thought and then fix that up. But thank you. I always appreciate that debugging. It's not the kind of I/O we're here to do, but I suppose it is necessary. So we now have an input history, and every time we do input and we copy the state, we say, wait, what's going on here? Okay, here. So input history equals input history dot enqueue input. All right. Autocomplete knows what we're after. And we can figure out the other bit later. But now we want to be able to show that history. So let's go back to main. Case input history. That's a bit too long of a command. Let's just say log, input log. Okay, and then, yeah, that's decent. So emulator will take the input history and we'll make string with those new, I think we do definitely want the new lines. No, I don't think we want new lines. I think we want to make this copy pastable into our code. So we're gonna just make it a list parentheses, comma separated, and then close parentheses. That way we can just copy paste it into Scala. Which means we also need to escape some quotes. Yeesh. All right, does that look right? Escaping things always makes it so confusing. No, there's an extra quote in there. Okay, escape the quote and then the closer parens. Okay, that looks right. Oh, what's going on here? We still have some compilation errors. Fair enough. I am using SBT run now, rather than SBTN, just because I found when I was using the SBTN in daemon mode, I found that you could close, if you close a program, then it disconnects the input. Then when you run again in the future, it's already closed that. Then you kind of just have to like reload SBT anyway, which is pretty annoying. Okay, let's fix the errors here. Missing arguments for parameter. Where? Here. Right, so this isn't progressed until blocked. This can really just be copy, right? Because when we progress to it, we don't do anything to do with that input history. So we'll make that be a copy so that we can ignore that parameter. Anything else? Okay. Let's get some history in here. So let's go go away, and then we'll go north. And then slash what was it? Input log. Oh, lovely. There are still new lines in there. But at least it got all the characters. So where was that in our show command? Oh, the commands all end with new line. So input history dot map dot strip. There we go. That should take out all white space, right? And then we definitely want to take out that info. It's kind of killing the vibe, isn't it? So let's go doorway, let's go north, and then log input. Oh wait, no. Input log. Cool. Including the misunderstood instruction. Alrighty. Now let's go back into the console. I can pull up what ChatGPT said, but I think WFM Macaw has our back here. Okay, yeah, let's learn a little bit about how this works. SBT's console pipeline is line buffered. Aggregates output into a new line before emitting, so flush won't even affect SBT's logger buffing. Oh wait, you started changing things. Don't change it. Okay, so stream forked run output directly to the terminal and disabled supershell so characters appear immediately. Looking true is already present. Output strategy equals sum standard output. Okay, so this is exactly what WFM Macaw was saying. Yeah, why use ChatGPT when you've got Chat Macaw? So let's take a look at that. So build.sbt. That's good. We'll keep that. And disable the SBT supershell. Does that have other consequences we won't like? Let's keep it for now, but we'll keep an eye on that. So let's reload SBT. Give it a second. All right, and now run main Synacor. There we go. Right, but we do need to handle the wrapping. Great. So we already have a function that's doing our type line, right? So we can count the number of times we print a character, and every time we printed 80 characters, we insert a new line. So bar column starts at 0. So for each of these, we print a character and then col plus equals 1. And if column is greater than or equal to 80, then nope, not that. Then we're gonna print a new line. We print a new line, and we also set column equal to 0. Okay. And if there's a new line otherwise, well, I guess if the character is a new line, then we also set to 0. So if character is equal to new line, then column equals 0. Okay. Did we do column plus equals 1 for all of these? Yeah. Okay. 80 is too big. So let's try 64. Okay, yeah, that's better. So now we can go north. Wait, no. Doorway. north, north, input log. There we go. Bridge, continue, undo, continue. All right, great. I'm much happier with that. And at some point, we'll do a full run through of the game, just so that we can get that whole input history. Yeah, because we want to get all the way to the very end and be able to very quickly start from that state. So we can run a version of the game where we just feed it all of that input and let it keep running. Maybe I should have, it makes me wonder that I should have like an input queue that I can choose to consume from rather than like requesting more. Oops/oops. Yes, it can totally just be oops. Case undo or /oops. Done. We have implemented an oops command. Right. Ability to replay commands. We are halfway there. We can show our log. So we need the ability to set the 8th register. And once we set the 8th register, well, okay, we do need to get all the way to the end in order to like mess with the teleportation box. So I think we do need to run through the game, run to the end, and get the teleportation box. And then we're going to save all that input so that we can start there quickly every time. Yeah, every time we start the game. And then we can start messing with the 8th register. But we were just in the REPL, so we'll add this ability, and then we'll go test it. We at least have the ability to like save the commands. So we'll go there, we'll go to the teleportation box, save those commands, and then after that we can figure out how to get there again quickly, because that's when we'll actually need it. So let's go back to our emulator. And now we have def set register. I think what I might want to do here is a function, just do set registers. So we take a function from registers to registers, because I think registers already has built-in functions for managing register state. And wait. What? So the time when we'll want to set registers is usually going to be a time when we are waiting for input, isn't it? Because that's when we'll say, hey, set registers. So currently, our input tick does not, I'm not sure I like this code. Yeah, I don't like it. Certainly in the continue, registers F, VM not registers. Yeah, certainly in the continue, that's what that would do, but we also want to be able to do that in the input, specifically in the input, right? Like we do it anytime. And that is not dead code. That is absolutely not dead code. That is a lie. I think it's telling me to write dead code elsewhere. That's like, okay, I can just declare that anything is dead code. Lie. That's not great. You don't want your I doubt I'll ever be able to trust an LLM to accurately determine that code is dead, because that's sort of the halting problem, isn't it? Um, so you don't want it saying that. That's kind of funny. Right. Before we do this, We need to go to our ticks. And what is the consequence of doing this? So input. We do want to have our current state, and we want to have a function from character to state. And how is that used? Let's look. Def input. Oh, well, we're not using it here. Where does that get used, actually? Let's look at the emulator layer. Okay, so input. So we're given an F. So there's a state here that we're going to ignore, right? We apply F to the character to get a state, and then tick. Because what this F does is operate on the state. So if we say state, VM state here, or no, it's what is the current state of it? I suppose it is ready. Yeah, when we input, we are in a ready state. Def input. Oh, no. Okay, so in the place where this is used in the emulator, so this is why I don't like having this state here. Or at least I don't like it in this way. Because input also gives us a function from character to VM state. We're constructing this function here, and we're saying based on that character, you're going to do this to get your next state. But this, when we do this, we're doing it to this, right? We're not doing it to the state in question, or to the state that's being passed along. I suppose if the function is being used by our state machine. No. It's not being used there. The function is being used up here in our emulator. So we call this function on RC to get the next state. Right, and if this is an input, then there's a state here. We still call the function on C. But this function here that we're given will always operate on this state. So like the issue here is that the state could be completely divorced from this F, right? This F is going to operate on a state. It's not necessarily this state. And so now that means that we've created a way to create inconsistent state, to create bugs, and we want to make those things not representable. So I think I will go along with this, but if you have thoughts for removing that and making it, making the type system nice here, then let me know. Yeah, when we're not able to solve it, that just tells me that there's something about our program that we're not understanding properly. That should be solvable. Okay, so that digression is done. VM state, we'll leave it as a to do. So this input, we're constructing it now. we have, I suppose this, right? It's on this input to say this. And then there's this function that we're passing along. And the constraint here that we want to enforce is that this is the very same as this. You know what? I think there might be a way to do that. So if we look at input, um, so we could do this a function from character. Uh, I think you can do this with a singleton type. So this is a function from character to VM state. But maybe what we actually want, well, it still needs to be a function of character, right? Because we're telling the outside world how to get the next tick from a character that the outside world itself is supplying. But maybe it's this to another VM state and we just query this function. Maybe it's queried. Okay, I'll sleep on that. Maybe someone in chat knows what to do there without thinking too hard, but we don't want to get too stalled up on that. The point of this whole thing was to enable writing this. So set registers, we look at our current state and we match, and the case that we're actually interested in, the case that might happen is tick.input state in F. So now we'll set registers. We have a new state, right? Copy the registers with the F function exactly. I'm gonna rename this to new state. And the same kind of thing happens for output, right? So let's go back to our VM state. So case output. And again, there's a character. I think, well, okay, in all these other cases, VM state is always last. I think, well, except continue. I think if they all have VM state, state should be the first parameter, right? Well, actually, I kind of like using I like using the right channel for the updated thing. And then the left channel is the extra thing. So we'll do that. Bob, no. Oh, you're starting the Synacor challenge today. You just got your VM running and then was dropped into the foothills. Great. I'm glad you're doing it. Um, yeah, I hope you have a lot of fun. Oops, we don't need this anymore. Okay, so we're now able to set registers. And now let's go to our main loop. And we'll set register 8. So let's do n match. Let's turn off that copilot. So let's look at the 8 case. And the others we don't care about for right now. So now we have emu dot set registers. And this register function, we can do dot updated. No. Oh, we could do it that way. Yeah. Dot updated is an option. What else do we have? Well, we have this nice method for applying registers. So this is where we pass an actual register. So that's not exactly what we want. But we can do registers.copy. We don't have a copy. We can do something like this. So def and for each of those that is set, we can default all of those to their current values. I don't like this necessarily because we are updating multiple. Yeah, I think I'd rather just index into it. I would just rather index into it. So we'll need import numbers. That star val r8 equals. We should have these set as constants, but the value is going to be u15.max value to int. Oh, do we have a way to get it as an int? As index. You know, let's do this the right way. So we'll go to our numbers package, and where's our definition of register? Okay, so object register, and we'll hard code these as the 8 constants. So val r8 equals this first value here, 8, 4, 5, 6, 7, 8. All right. Whoops. Okay, so we have 1, 2, 3, 4, 5, 6. I'm sure there's a macro for that. And then these numbers here, and the rightmost numbers here, and the top one is 0. Great. We will need those constants. So no need to try and hack it. So we're going to set reg.r8, I suppose. Numbers dot reg.star. And we're going to update that with a value. So we set our blank to n, to something. And that's something, how would we input it? We could input it just as a number, or like, I think we might actually want it in hex. Well, first, let's change this to index. So that's the index. And then the value, we're going to make n. So n dot to int And we've got word. Okay. So numbers.word.from int. Yeah. It's a little verbose. I feel like I probably have a nicer way to do that. Already, because that's something I've had to do often. Don't we have an int.to? Let's look at our numbers package. Is there an extension on it anywhere here? Okay, like we have a toLit. So extension on register on lit. I think we would want it to be a lit anyway. We wouldn't want it to be an arbitrary word. Okay. So we'll do n.to int.to lit. All right. Um, oh, right. That's the R8 case. We're not going to worry about anything else. So we'll do like a I.toInt match. And now with this, oh, it seems I'm frozen. Okay, so now with this, I think we can restart the game. We can run all the way to R8. Well, first we make sure that we are able to set that correctly. But then we can run all the way to the teleporter, pick it up, save our state, or print out our state, and then we can try messing around with the R8 value. Oh, right, we do still have some type errors in here. F does not take parameters. Wait, we've got backwards here. It's F followed by state. There we go. Where else? Copy is not a member of character. That's because that's also backwards. Okay. Where else? New state. Copy registers. F should be a function on registers, right? This is a function on characters. Yeah, we're not supposed to be using F. So say that copy registers. Oh, we need the outer F here. So this is the advanced, I guess. Okay, we still want that F there. And then we copy this next. I don't like doing it that way. I think what I want to do is in, at, which is a tick.input. So in.state.copy registers F on the registers. And then we copy that state. We copy our Yeah, state is just equals the new in. I like this better. So that's kind of Copilot taking us in a direction we didn't really want, wasn't it? Okay, yeah, we just take our in state and we copy it with the registers modified. And drop that line. I think it's pretty understandable without. And technically, we would do the same thing for output. And this should work for any of these. So tick dot input, tick dot output. So for either type, we could just call it tick, right? And what are we copying? We're copying our emulator. Oh, I suppose we need to copy our tick too. So state is of type VM state, or no, state is of type tick. Yeah, as is a tick. Where were we? So case tick, this should be an or. So if we're either of those things, then either of those things has a state, right? Does that compile properly? State is not a member of tick.input or tick.output. Okay, fair. Fair enough. Right, that's not how union types work. We need lenses here to handle all this nested copying. Yeah, that kind of gets gnarly, doesn't it? So it's the same code if it's whatever the type is, right? And it's the same thing if it is output. And then it's all we're not gonna worry about it. Pick that state registers. Okay. All right. It isn't the prettiest to look at this way. To make this syntactically pleasant, we need a thing called lenses, which lets you compose deep mutations like that. Because we are an emulator, we are changing our tick and changing the internal VM state and changing the register inside of that. So we have a deeply nested immutable structure. And this is what happens if you don't have the tools to deal with that. Okay, but we do have it. Excuse me. No, we still have type errors somewhere else. So we required a reg somewhere. We found an R8. An R8 is not necessarily a reg. Interesting. Oh, R8 is of type int. Val R8. Oh, yes. These need to all be listed as register. So we'll say no, colon reg. Value 2lit is now a member of it somewhere here. Synacor numbers at 2lit. Found lit. We required a word. Oh, update requires a word, but this update method on a, give me my second. Okay, yeah, I think we did decide that a register could be updated with an arbitrary word value. Because it didn't, the architecture didn't necessarily specify, or the architecture spec sheet didn't necessarily specify it. Toolit is not a member of int. And the extension method was failed because we found a lit and we required a word in this update method. But a lit should be a word. So let's look at our numbers package. A lit is a U15, and a U15 is a word. To lit. Right, so that lit should be a lit. But that lit should also be a word. Okay. Oh, and we're getting a helpful warning here. Right, this thing had a value, it wasn't unit. So this would actually have caught a bug earlier when we were not consuming. No, not that particular case. But basically, we should say emu equals there. We're discarding the value. We actually want to use that value. To lit. There we go. Found lit required word. As word. So we should be able to widen that. I thought a lit was always a word. Oh no. W Lord. Wow, how long has that been there? Oh, that must have been just now. Let's try that real quick. Pile that. That's a lot of error message with not great syntax highlighting. Okay, so we can just take the word this way. So I'll leave that commented because I want to go back to that val word equals word dot from int and dot to int. And we'll update with that word. Okay, what are other issues? Has moved. We added an extra A in there. Yep, there's a lot of green. And I did at least try to make some, like this year's red. And I went through some like other colors, blue and yellow and whatnot. So I remember having more colors than just these. But I don't know, I'll have to debug that again because I'm only seeing 2 colors here. And I'm pretty sure SBT has more than 2 colors. Okay, I see 3 colors. But I was using a full palette of shades of green. Okay, so here's the next issue. This is in the wrong order. So we put the function first, and then this here. Required. Ready. But this is ready. We have proof that this is ready. Um, right. I guess we could just say that ready. I wonder why that is. Oh, you know what? This here is this does give us a function, doesn't it? Using ev is ready. Ev.apply. Oh, no. That doesn't work. It turns a P into a ready. But we're not actually acting on a P. And I didn't do this. I'm gonna look at this again later. Or unsafe set ready. Unsafe set ready. Do remove unsafe. All right, get that out of the way. We're not teaching our type system properly if it thinks that's unsafe. Okay, so we should be running now. Okay. So from here, what we're gonna do is run through the game and then save that state. Oh, but first let's make sure setting R8 works. So our command, what is it? Set R8 to something like 123. Did I need to type 2 enters there? Help. Okay, let's look. Okay, we can do that. Undo. Okay. Great, let's try that new command. So set R8 to 100. Oh, right. And then from there, right. So it does do that. And then from there, it's back to waiting the command. So I suppose maybe after we do this, we should just send the look command to, yeah, I think after we set to register, we just set the look command to the actual game. Okay, so emu equals emu dot, how do we do it normally? Where is our base case? Here, command. Emu dot feed. We're just gonna feed the look command new line. That's more readable. Okay, so now we can do something like, you know, we need to be able to look at the register values. So let's also add a get in here. So get R8. In fact, I'm just gonna have it specialized to that because we're not gonna care about the other registers for now. Everything else can be a match error. So this is get R8 value N. And let's see how we would do that in the VM state. So we can just take emu.state dot wait. I suppose we need to match on this. Let's go to our emulator layer. Okay, so we can set registers in an emulator. I think that function should actually be done at a lower level. But let's do a get register. Okay, so get register, and then we have a reg value numbers.reg. And this just returns a value, a word, right? And we can do the hex on that. So now we take our state dot, well, state match, I suppose. So take our state match. So if it's an input, continue, or output, that's all we'll care about for now. We're not going to worry about a halt yet. Or actually, what all we really do care about is input. So everything else will send there. Tick.state.registers dot r dot apply. We just apply it to our reg. Okay, that does the trick. And numbers upward. All right, now our get register. Here we can do emu.getRegister numbers.reg.r8. So there's the word, what is that? And we can print that. So register 8 value is, oh, and we're not going to print line, we're going to type line. Type line is word.text. Okay. And in this case, since we typed something, I feel like it's straightforward. We don't have to do the same thing here with a set where we just feed look back in. So try that out. Let's see how that performs, how that feels. Okay, so let's go through the doorway. Let's let's get R8 first. Get R8. Oh, why is there a number parameter? Let's remove that. Get R8, and then, I don't know, 1, 2, 3. This is the default register value. Wait, no. That was me trying to do a formatting string. Let's fix that real quick. So there's a formatting string. We'll give it a comment. Hex string added to 4 digits, I guess. And Copilot, this is where you shine here. Beautiful. Oh yeah, I didn't even think about the masking. Well, the masking is not necessary because we're already confirmed that this is a word, right? So it shouldn't be necessary. Okay. But that's what that would turn into. So it starts at 0. So let's set R8 to 1, 2, 3. Let's get R8. And the value is still the same. So we did something wrong there. First, let's take off this in our get. We don't need that parameter. All right. So get register value. Valid word equals new get register, sure. And then we continue with the loop. When we set register, we do reset the value to even. And when we set registers, like we are changing things, right? Like we're calling, yeah, we're calling our register changing function on the registers. That looks correct. Also, don't we have, I don't know. So we're updated with a register and word. And update, we update the underlying index at R. That seems pretty straightforward. I don't see room for error there. And it looks like the rest of our state is still updating. North. North. Bridge. So let's try that again. Get R8. Need to pass a parameter. Well, actually, let's just recompile it with the new updates. Okay. Get R8. There's the register value. Go away. So let's set R8 to 42. And we look again. Let's get R8. Okay, so we need to do a confirmation. Let's add in an assertion there. So in our emu.setRegisters method, so val f equals that, right? And we're gonna return that f. But first, yeah, in the game, we want to be able to set the value of the register. And again, the whole point of this is that in the game, we can enable teleportation, so we can break through the game. But those don't be. It doesn't seem like we're setting those appropriately, so we're going to do an assertion and check that. No, not f. Right? Yeah, f. Dot state dot. F dot state dot state, I suppose. Dot where are my? I don't want Copilot in here. I want my actual type system here. Okay, so oh, I shouldn't have used F. So here is the new emulator state, right? So these are what we're returning. Okay, so the emulator has a state, which I guess is a tick. I should just rename that to tick. That state. And a tick itself has a state, which is actually a VM state. Depending. Oh, we can just take our tick. Oh, no. So that's our new tick. Our new tick is not necessarily an input. Well, this copy should... This copy method should give us another input tick. Val new tick. Let's do it this way. Equals tick.copy. Okay. And then in the end of all of this, we do E or whatever, this.copy state equals new tick, right? We might need to check our new tick, which I think it should also be an input. Yeah, our new tick is an input tick. So let's do new tick dot state VM state dot registers R8. Or let's just show that because we don't know what exactly we're asserting here, except that that function has changed. So we'll just print that before and after. So registers dot underline. So we're going to map each of those. So we'll map each of those to hex and make string with comma separated. So we'll do that with tick and new tick so we can see before and after. And then we say print line register updated. All right, go back to main. We're not going to do this thing where we feed look to the emulator because that's just going to be too much noise. And let's try that again. Okay, let's set R8 to 100. And it did not print anything before saying register updated, so let's see what's up with that. Yeah, because we didn't print anything. Okay. Great. Set R8 to 100. Here's the registers beforehand, and here's the registers after. Now if we, okay, so we see that is update get R8. Huh. Okay, I think when we were rewriting the code, we must have made the code not buggy. Okay, so whatever this code was that we wrote, we're gonna just copy it into the other cases because apparently it's more accurate. Okay, so we're able to do that. Now we can finally go through the whole game and go find the teleporter and save all of our state from there. And we can try messing with the 8th register before running a teleporter. And we still want to be able to, well, from that point, at least we'll have directions to get there. And then we could restart the game at that point. And from there, we can start looking at the bytecode that's running when we use the teleporter. So that's the part that'll be interesting. That's probably what we'll be doing most of the next session. Yeah, let's do the next 5 minutes of just running through the game. So we'll start that fresh here. So we complete the self-test and find ourselves in the foothills. We can ignore the tablet. Let's go straight through the doorway. Let's go north into the darkness through the cave. And let's go north some more. And now there's barely enough light for to see us a rope bridge. So let's go on the bridge. And from here, we continue, in spite of it being shaky. And then we fall down because it snaps. We have no choice. Now here, we need to go east first to pick up the lantern. So we'll take the empty lantern. Then we move on west through the cavern, moss cavern. Oh, whoop. No, passage. Into the passage. Dark passage leads further west. Okay, this is the ladder. So now we need to go down the ladder to find a can of oil in the twisty passages. So we go west into a little maze of twisty passages, and then we go south into a twisty alike of little passages, all maze. Then we go north into a maze of twisty little passages. There's a can, so we can take that can. We can use that can to fill our lantern. And now we can use the lantern to light it. Great. Now we go west, back to the ladder, and go up and out of here. Now that we have a lantern, we can go into the darkness without worrying about grooves. And continue. And we're going to keep going west, 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 through the dark passages. And one more west, and we're at the ruins. So we go north through a massive complex. There's a red coin. We'll need that. Take red coin. And we progress deeper into the ruins. Now we're where the monument is. We need to collect the other coins and plug them into this equation on the monument so that we can open the door that goes north to the teleporter. So let's look west. Here, there's a blue coin. We go up. We'll take this shiny coin. Then we go back down, back east, past the monument, east into the dining hall. Here's a concave coin. We'll take that. And then we go down the stairs into a kitchen. We'll take the corroded coin there. Oh, wait. Take corroded coin. And we'll go up and west back to the monument. Okay, so now we need to use our coins. And we've already solved this equation, so I'm just going to sheet ahead to that, we had blue, red, shiny, concave, and corroded. All right, we just gotta use those coins in that order. So we're gonna use blue coin, use red coin, use shiny coin, use concave coin, and use the corroded coin. And the north door clicks, so now we can go north. Now there's a teleporter here. But what minute we take the teleporter? Okay. Now this is a point at which we want all of our history. I forget what our history command is. Slash input log. So slash input log. Great. Now we can fast replay. Well, to teleporter. Yeah. I feel like we should be getting achievements when you do things like achievement when you cheat death or undo the bridge. I've been so trained by Steam games that every time I do something fun, I get an achievement. But no, all we can do is at ourselves. Ice Cold Witch, hello. Great. So we had a teleporter. Let's use the teleporter. All right. Well, we can read the strange book. So for everyone who might be just stumbling into the stream, and for myself, I like the strange book. Let's use a strange book. This explains the whole reason we're doing any of this at all. Oh, we have to take it first. Oh, I guess we look at the strange book. Ding. Yep. Thank you. I appreciate it. All right. Oh, you know what? This thing does have new lines of its own. That's unfortunate. I chose my new line length to be shorter than that paragraph. Well, um, anyway, here's that. A hypothetical such teleportation device would need to have exactly two destinations. One is a safe one. That's where we are right now. This is the safe default. The second destination is predicted to require a very specific energy level in the 8th register. We don't know what that is. If it is even slightly off, the user would probably arrive at the correct location, but would briefly experience anomalies in the fabric of reality. This, of course, is not recommended, which means, of course, we must do it. So let's try that. Set R8 value to 42. Them boys, yes, I'm still here. Where you been? We're about to experience I don't know, failed teleportation. So we set R8 to 42. Did that work? Did that do anything? Yeah. I forgot that I removed my confirmation message. Let's do get R8 just so you know. Okay. Yep, the register value is 2A. And now let's use the teleporter. You're sleeping in UK time. You're waking up at 6 a.m. every day for having a code? It would be 6 a.m. at midnight, right? How are you ever gonna catch me if um I'd have to like be up until 3 a.m. I guess you're just an early riser now. Although in all seriousness, I can't sustain this either. Come January, I'm gonna start a contract. I can't be doing midnights every night. I'll probably still do 1 week a stream that's midnight, and then I'm gonna find like a more reasonable time during the week. So I don't know, maybe like a Tuesday at 5 p.m. or yeah, Tuesday, maybe a Friday. Nah, I don't know about Friday. Sunday at midnight and Tuesday at 5 p.m. Something like that. Okay. Should I stop stalling? I'm gonna hit it. We use the teleporter. You see a pattern in the stars, which is different than the pattern we saw earlier, right? No, no, no. It's the same pattern. Okay. And we end up at Synacor headquarters. You stand in the lobby of what appears to be a really fun place to work. Yay. Sadly, there doesn't seem to be anyone around at the moment, so you make a note to call them later. The bookshelf here looks like it might have something interesting in it, though. Well, I mean, there's a business card. Let's just do that. Taken. Inventory. Look at a business card. Okay, I'm not noticing anything weird yet. Okay, I mean, you kind of jump scared me. Thank you for the follow. Go outside. I'm like expecting something weird to happen, all right? It's a warm, sunny day. While the breeze from Lake Erie is certainly refreshing, you don't see anything here that will help you with your quest. Nothing has changed. Get R8. Oh wait, it reset the value back to 0. Using the teleporter reset it back to 0. That's weird. Set R8 to 142. Get get R8. And then use teleporter. Okay, and then now I know, now we'll get R8. Huh, it reset back to 0. I'm not sure if that's like the expected behavior, or the behavior I expected rather. Well, let's read the book. Um, I'm not sure I like reading this in red. I'm gonna reformat this a little bit. I don't know, make those strings up. We'll get rid of that info message. Yeah, let's make them strings. There we go. Now we can read in pleasing CRT green. Oh boy, we need to escape quotes. Is that all? Oh, for fuck's sake. Okay, no, we don't need to do it that way. There are triple quotes. Oops. Yeah, we wrap that in triple quotes, it escapes all the quotes. There we go. Okay, so what did we miss about this here? Any teleporter would need to test the energy level and abort if it is not exactly correct. Okay, that's what we're missing. So it does abort. It aborted because it wasn't exactly correct. This requires this required precision implies that the confirmation mechanism would be very computationally expensive. Okay, so it starts doing the computation and it's at least able to abort early. But I imagine like confirming that it's correct would take longer. Yeah, a handheld teleporter would need billions of years to compute. So we can't do that by brute force, at least not within the Synacor VM. We have to re-implement whatever the algorithm is. Okay. You know, that's a very good question. It's like everything is kind of like CRT themed. There's like shades of, and its common is just red. Every other color scheme makes comments like hidden, you know? Like this. This is what you want comments to be. But they're like, you have to be able to read the comments. It's like shouting at you. But yeah, good question. Very unusual. Okay. So we've been able to play the teleporter. We've been able to test the abort mechanism. Um, and I think that abort mechanism we can play around with. So I think the next stage from here would be um, to start outputting assembly code or at least addresses of where this is happening, and then reading the bytecode. This does have a satanic vibe to it, kind of, yeah. I know, right? Same hue but faded. Let's go back to our README and see what we're doing next. Okay, we have the ability to set the 8th register. Yes. We don't yet log the running bytecode and PC location between two states. We don't yet disassemble bytecode into something readable. But I think those are both reasonable next steps. Ability to replay commands. We at least have the commands that we want to replay. Okay, so I won't jump into this yet, but I think a nice way to end for the night would be to get this replay ability here in play, and then start playing with it in a worksheet, right? So if we have that fast replay, then we can just set up an emulator state here. We can set it to where we want it to be, and we can just interact with it live in the worksheet. And we don't need to do it in the REPL where we're sending all these ad hoc commands, right? Because now here we have full power, and it's not just whatever we defined. Because I think for these next couple of steps, we'll probably be doing a lot of like exploratory programming. Right? Yeah. We'll do, I don't know, we'll be like pulling out the memory and searching through it, things like that. So let's go to the emulator and let's add a way to replay commands. Hmm. So this will just basically build out a huge output queue. So def feed multiple. I suppose, no, I do want to have it at the layer here of the emulator because we want to use the emulator in other places. So replay, no, it's not even necessarily replay. Feed multiple. So this is inputs, and it's going to be a list of string. And we get a new emulator state out at the end. And now we can basically take our inputs, and this is a fold left. Inputs.fold left. So we're starting with our current state, so this. And then we're folding on We have an emulator state. I hate that I've named everything state. I should really call that tick. So we have an emulator state, and an input. Now we should take that state and progress until blocked, and then feed that input at each step of this, right? And then as that's happening, the output queue is continually growing, the history is being saved, etc. Yeah, well, that's that. And then we can just dump all the output queue. So let's just try loading up a game where we start with everything we did from last time. So like we can dequeue everything but one and just get the last one, right? Let's go to main. We have our to teleporter list commands. So our shortcut. In fact, let's call it that. Shortcut. And now we're going to take our emu. I know. Let's do it here. Emu dot input. No. Feed multiple. And we pass along that shortcut. And then let's get the last. So emu equals emu dot feed multiple. Emu dot output queue dot last. So that's what we want to replay. So let's type line. Type line, yeah. That last one. And let's say emu equals emu.copy, where we have an empty output queue. Output queue equals emu.output queue, or no, just an empty. So queue.empty. Yep. We need to import that mutable.queue. Wait, no, collection.mutable. Okay. So now we have a shortcut. Let's do that. Assertion failed. Okay, we broke one of our invariants. We violated something. During feed and feed multiple, inside of feed. So we'll look at our emulator. Def feed. Oh, right. They all need to end with a new line. Okay, shortcuts. Shortcut.map plus new line character. There we go. And actually, I think instead of just retyping the last output, yeah, I think instead of retyping the last, actually, we'll copy this here. We'll make the output queue empty. I guess we could add like a clear Q command. Beard Ninja, thank you for the follow. We can just do a look command. So emu dot feed look. Oops. Yeah, after running the shortcut, we look. And this whole bit here together, I might just make that a method run shortcut. I don't know. All right. So now we can run that. What's wrong here? Exception input too long. Oh, huh. That's funny. That's another invariant that I thought we would never violate because we are doing things differently. So input too long. So this is a case where what happens here? So there are still more characters to do, even though the tick. Huh. I actually don't expect that. If characters are empty, then we return the tick. So we found a new line, and then we didn't. Well, we had this assertion that everything only has one new line, and it is at the end, right, of the string. So somehow we ended up with empty characters. So we're looping on these characters, taking them off one at a time. And our characters were not empty once we hit a tick that was not just input or continue. Right. Because I suppose we had the assumption that we're doing output too. So this is a case where, don't you mean the red and green? Kind of, yeah, totally. That makes perfect sense, actually. So this is a case where I think we're kind of discovering constraints on our emulator, right? Do you remember in our VM layer, VM state? So you remember here, there's like a state machine during like the sub phases between ticks, how first you have to be ready, then you have to be updated, and then you have to be moved, right? And you can't re-ready until you have moved the program counter. So there's an assumption here that we do one after the other. And we haven't encoded that assumption in here. And the reason I like to do this, I don't know. I don't feel like we've really yes, it's working, but I don't feel like we really solved it properly until like we distilled the model. Which is to say, like the reason that the way I like to interact with the type system is like I'm teaching the type system what I know, right? And then I start so I encode some of my constraints, some of the things we discovered, the invariants to constraints, into the type system, and I start working within that new system. Then while I'm working that system, it's kind of the type system's turn to teach me. It's like, oh, this is what you don't still know, or turns out this is a thing you can do, right? So it's not a thing I might be able to think about without like a formal approach. So the formal approach makes all the things that I think about this formal enough to test and see that either the thing that I think about the program is wrong, or the thing is, or there's like another thing I didn't even realize about the program. So that's why I do that kind of thing. Because like obviously, the fact that we're running into an error here means that like I have uh, I've made some sort of assumptions. I haven't formalized them because I'm unsure. And if I were sure, that would already be in the type system, right? So I don't really ever feel done until like I've distilled it, like it is over here. The VM state feels very done. This feels very easy to work with. The emulator, I'm still kind of figuring out what exactly the emulator is, right? We know that does a few things, and that's all we really know. Um, anyway, we are we are solving a bug. As a a digression, I suppose. What I thought about what was actually wrong here. If you see it, let me know. But back to the error. So we have an input too long. Okay, somehow we got to this thing that I marked as dead code. Dead code is as far as I got at formalizing this. So we have an input, and we tick through, we loop through here. So we're looping through all the ticks, one character at a time, and we see continue, we see input. What happened is like in any other tick, then we assume we're done taking input. So what we probably saw was an output. So we could also build an output string while we're doing this. But I think the greater issue is that um, assuming that the input stretches in the Synacor game are all well formed and behave properly, there shouldn't be actually be any output. So feed assumes that we first call progress until blocked. And here, instead, what we're doing is progress until blocked and then feed. So after all of this, we need another progress until blocked. That's actually pretty easy to figure out. So here, val emu equals. Oh, thank you. Yeah, it's actually another. It's one of the things I've been liking about doing this Synacor stream post advent of code. In advent of code, like you kind of rush to finish things. Here we can take our time and you know we can think through things. We can talk it over. You can spend time like doing design, which I've been very much enjoying. I've really appreciated it when people like chime in and say like, "Hey, that's not a great idea," or "Hey, here's your bug." I really love hearing that. um, and that's not a thing that happens as much during advent of code because you're not supposed to spoil people as much on there. So emu dot progress until blocked, and then we can feed. All right. And if these things had like a state machine inside, we could enforce that we are in one of two substates, either printing output and doing calculations, or intaking input. Then we wouldn't be able to write code that didn't have this line here, right? This would always be alternating. So I'll do a to-do. To-do, alternate between in, out types. Yeah, exactly. So having done that, taken, what we do? Well, let's look. We are at the ruins. Wait, this isn't where I expect it to be. Oh, no, yeah, we are at the ruins. This is, I think I expected to look here. So we we progress until blocked. Use output in type line. Weird, I had to look again. Oh, at that point, I see. What do you do? Hmm. Anyway, hey, that worked. So we went right for the ruins, and we can use a teleporter. Cool. All right. Let's go back to our README. Ability to replay commands. We'll give that an X. We were replaying commands. That's really probably the only thing we want to replay for now. But we at least have a feed multiple for future reference. Ability to rewind state, emulate at a higher level. Yeah, this is kind of like a meta to do. Set the 8th register. You can absolutely do that. And this stuff that's remaining. Okay, so I think we've done good work, and this is a good place to call it a night. What have you done tonight? So I'll fill out notes for. You know what? Let's do some notes here. Let's do some notes live. So this is for part 5. What did we do today? Well, we can see it from basically our Git diffs here. So we added the ability to undo commands. Added a command history. We added the ability to replay a history. So basically we've unlocked time travel. And what else is in here? And we did some refactoring. We didn't do heavy refactoring with the emulator. But set register added ability to set get register and tried teleporting with a different register value. Okay, cool. So not bad. I'll be on tomorrow night at the same time, just before midnight. And then we get to dig into some actual bytecode. So we'll do a disassembler. We'll look to diff between two different snapshots and look at what changed between those two in order to find that bytecode. And if it takes us, if we can do that fast enough, we might even get to start to reverse engineer that bytecode. Yeah, I appreciate you being here. Thank you. All right, shall we find a stream to raid? If anyone has suggestions for a raid, I'm always happy to take that. Yeah, I'm also excited to see how I'll do that because I barely have a vague idea right now. I'm glad you're finding it to be like a cool new paradigm. Okay. Well, there's no more advent of code. So at this point, we're in territory where I don't recognize. Oh, is there advent? Oh, is that adventure? Yeah. Oh no, that's me. Um, yeah, I'm on the side of Twitch I'm not familiar with. Code's building a volumetric rendering application. Is anyone doing anything in assembly? Because that's adjacent to this. We're gonna be doing assembly next time. Oh, okay. Building a volumetric what? Rendering application? Maybe. Let's look at the first couple. What did you have for lunch? Rust and Godot. Refactor and cleanup stream. Oh, we like refactors and cleanups. We can see what Sergeant Pepper is doing and what they can teach us about Rust refactoring. Yeah, let's see that. Raid S9T Pepper. All right. Thanks, everyone. Ice Cold Witch, Suno. Have a good night. Sparkly Dark Matter. Them boys. And WFM Macaw. Good crew regulars. All right. Let's see some Rust refactoring.